On this page we have graphs of 12 functions that we call parent functions because they are the simplest version of the type of function named under each graph. What I want you to do is, using the definitions of odd and even discussed in the previous video, pause this video and identify each of the graphs as odd, even, or neither. Then turn back on and check your answers, and we'll discuss why each one of them is odd, even, or neither. Okay, the first graph is even. The definition of an even function is that opposite inputs give you the same output. So if I take, for example, 3 and -3, they both give me the same output, and that's true for any pair of opposite numbers here. Second one is odd because opposite inputs give me opposite outputs. So if I look at 1, 2, 3 here and -1, 2, 3, notice that their y values are opposites of each other. The third one is even. Opposite inputs give me the same output. Another even, same thing. Opposite inputs give me the same output. Odd, opposite inputs give me opposite outputs. Another one, odd, opposite inputs give me opposite outputs, and it's the same for any graph. Now the next one's neither, because if I do opposite inputs, I don't get anything over here, either the same or opposite. There's nothing there. The next one's odd. Opposite inputs give me opposite outputs. Opposite inputs give me the same output. And then the last three are neither, because they are neither symmetric with regard to the y-axis, nor are they symmetric across the origin. So you can see that they have neither opposite inputs, same output, or opposite inputs, opposite outputs. So another thing with even is just the symmetry on the same on both sides of the y-axis. So that's another reason that you could have identified the even ones. The odd ones have that symmetry through the origin, that they look the same, kind of flipped over in opposite quadrants. Now the next thing I'd like you to do is go through and identify all of the graphs that have all real numbers as their domain. Once again, pause your video, try it, and then turn the video back on. It turns out that the majority of the graphs have all real numbers as their domain. Notice here we have all negative number values for x, all positive values for x, and 0 for x all correspond to some number on the graph. Here we have positive numbers for x are represented on this part of the graph, negative numbers for x on this part, and then 0 for x. Same thing here, positive and negative and 0, positive, negative, and 0. Here positive numbers give me positive x values, negative numbers give me negative x values, and if we were to go out really far and go up really, really high, we'd always find a point on the graph. So all real numbers. Now we get to the reciprocal function and we find out, no, there is a missing value. Right here, when x is 0, there is no number on the graph because there is what's called a vertical asymptote here. Basically, we could draw sort of a dotted line here, and the graph would not cross that at all. It just runs alongside it. So we have a different domain here. It's everything except 0. So the way we would write the domain here is we would write this negative infinity to 0, or 0 to positive infinity. So there, notice x cannot equal 0 because this is 1 divided by x. X could equal anything else except 0 though. This one is two others that are all real numbers are the cube root function, we have values in the negative and the positive direction in the x direction. Here the two exponential functions. This is going up, but it's still continuing to gradually go out, very gradually. But if I go over as far as I want in x and I go up very, very high in y, I would still find values. Here, if I go to the left on the x-axis to the more negative values and go up really, really high, I would still find a y value. So all real numbers here. So the reciprocal or the square root function, we know that if I take the square root of x, x has to be 0 or positive. X can't be negative. So x is only 0 or positive. So the domain here would be 0 to infinity, only 0 or positive numbers. Here the reciprocal squared function is just like the reciprocal function in the domain, is that there's all these negative values for x and positive, but x can't equal 0. There is an asymptote here, so it has the same domain. I'll do this in blue to keep everything the same color. It has the same domain as the graph directly above, negative infinity to 0 or 0 to positive infinity. Now the last one, the logarithmic function, it has an asymptote also on the y-axis, and notice there isn't anything on the negative side, so x can be positive, x can't be 0, so it's very similar to the square root graph except for that x can't be 0. So this is a logarithmic function, and we'll talk more about those later. This is just kind of the shape that I wanted you to look at right now. So 0 to infinity. Okay, so let's talk about range. What I'd like you to do now is go through and mark anything that has a range of all real numbers. Okay, there are fewer that have a range of all real numbers. This line does. You can see that we go all the way up in the y direction, all the way down, and is continuous. There's no breaks in the graph, so this would have all real numbers. Same thing with this cubic function. Okay, it goes all the way up and all the way down, no breaks in the graph. Let's see, any others? This one, you might not believe this, but it does continue to go up very, very gradually. Very gradually, but it's going to continue to go up. So if I went up really high on the y-axis, or even up a little bit high, and I went far enough out, I would find another y value. This is going to continue to go up, and this is going to continue to go lower, higher and lower. So eventually we get to all real numbers. It's just going to go very gradually. And this one, you can see that it's going down. The graph is running down this direction along the y-axis. So there's the negative infinity, and then it's going to continue to go up. So eventually we'll get to all of the positive y values. Okay, so let's look at some of the other ones. This one is just a horizontal line. So the only value for y here is y equals 3. So the range here is just the number 3. Here we can see that square root of x, well, we can take the square root of 0 and get 0, but anything else in the square root is going to be positive, so it's going to be 0 or anything positive. So the range here is going to be 0 to infinity. Okay, so the only possible y values are positive or 0 because of the square root. Here we have f of x equals x squared, so we have the same thing. X could be x squared could equal 0, but anything else squared is going to be positive. So we're going to have 0 and all positive numbers. Now this one's a little different. It has an asymptote here. We see that we've got all these positive y values up here. This is where y is positive. Here's where y is negative. But y can't ever, the graph never touches the x-axis, so y can't ever be 0. So the range is the same as the domain. So I'm going to put the range is also the same thing as the domain. Negative infinity to 0 and 0 to infinity. So that just x cannot equal 0, y cannot equal 0. Okay. Now domain range here. Notice we could take the square root of 0 and get 0. And then we're only putting positive numbers in for x, so square root of anything else besides 0 is going to be positive, so y is always going to be positive. And you can see that the entire graph is above the x-axis except for that one point, so all of our y values are positive. So it has the same range as it does the domain. So the range is 0 to infinity. This graph here has only positive values for y, but it also has an asymptote on the x-axis, so y can't equal 0, but y could be any positive number. So the range is 0 to infinity, but not including 0. The range for both the exponential growth and decay is also 0 to infinity because we have an asymptote here. The graph runs along the x-axis but does not touch it. So the range is 0 to infinity, not including 0. You can see that there's nothing below the x-axis here. We've already talked about that one. So there's the domain and range of all the parent functions and whether they are odd or even.